let's find the limit of this sequence. Square root of 2, 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 and so on. Okay, so in order to find the limit of this sequence, we have to first find the general term of this sequence first. And how do we find the general term of this sequence? Well, let's take a look at this. Now, first of all, we need to write out the first few terms of the sequence. And you can see the first 3 terms already. And based on the first 3 terms, you can probably tell what the next terms will be. Okay? So the first term we will call this a sub 1, and that is square root of 2. Now second term, a sub 2, that will be square root of 2 times square root of 2. A sub 3 would be square root of 2 times square root of 2 times square root of 2. Okay, so what would a sub 4 be? Would be square root of 2 times square root of 2 times square root of 2 times square root of 2. Okay, what would a sub 5 be? That would be square root of 2 times 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 square root of 2. Okay, what would a sub 6 be? That would be square root of 2 times 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 square root of 2. What would a sub 7 be? That would be square root of 2 times 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 square root of 2. Okay, I have a reason as to why I will write that many terms out, and I will explain later. Okay, so what's a sub a going to be? Will be square root of 2 times 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 square root of 2. 1, 2, 3, 4, 5, 6, 7, 8. So basically, whatever this subscript is, that is how many 2's we have here. Okay, so what's a sub 9? That will be square root of 2 times 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 square root of 2. So 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay. Okay, that's it for now. Okay. So how can you find the general term of this sequence? Now let's look at how we can relate a sub 2 to a sub 1. Okay, so a sub 2 a sub 2 here is square root of 2 times square root of 2. Now, you can see that this square root of 2 is just a sub 1. So we can write that a sub 2 is equal to square root of 2 times a sub 1. Okay. Next, a sub 3. As you can see, this portion here, the square root of 2 times square root of 2, is just here, a sub 2. So we can write that ace of 3 is equal to square root of 2 times ace of 2. Now, ace of 4. This portion here, square root of 2 times square root of 2 times square root of 2. That is just here, ace of 3. So we can write that ace of 4 is equal to square root of 2 times ace of 3. Now next, let's do one more. Ace of 5 here. This portion here, square root of 2 times square root of 2 times square root of 2 times square root of 2. It's just this here, right? Which is ace of 4. So ace of 5 is equal to square root of 2 times ace of 4. Okay, let's stop here. Right? Because if we keep going, the result will be the same, right? The pattern will be the same. So as you can see here, the subscript on the left side is always one higher than the subscript on the right side, right? So this is 2, 1, 3, 2, 4, 3, 5, 4. So we can write the general term of this sequence now. General term of the sequence. Okay, as you can see here, we will write the right side first, right? Now, we have to make sure that our first term is ace of 1, okay? So n has to be at least 1. So n has to be greater than 1 or equal to 1. So in this case, since this is having a lower subscript, we will write the right side first, okay? So we will write this. On the right side, this will be 2 times ace of n. And the left side, as we discover, the subscript is always one higher than the subscript on the right side. So we will write that as ace of n plus 1. Okay, so that's the general term of the sequence. Ace of n plus 1 equals to square root of 2 times ace of n. Now, the original question is to find the limit of the sequence. Okay, in that case, we will take the limit on both sides as n approach infinity. So limit as n approach infinity, ace of n plus 1 is equal to limit as n approach infinity, square root of 2 ace of n, or 2 times ace of n. Okay, now looking at this, as you can see that this limit here as n approach infinity will only apply to ace of n here. So I can rewrite this as limit as n approach infinity, ace of n plus 1 is equal to square root of 2 times limit as n approach infinity, ace of n. Now, at this point, we don't have enough information to calculate or figure out what the limits are here, right? So what do we need to do next? We need to calculate the value of the first few terms and see how the behavior of the sequence is like, okay? So if you put in the calculator, ace of 1, which is square root of 2, is approximately equal to 1.41, okay? So this is rounding. Ace of 2 is approximately equal to 1.68. Ace of 3 is approximately equal to 1.83. Ace of 4 is approximately equal to 1.92. Ace of 5 is approximately equal to 1.96. Ace of 6 is approximately equal to 1.98. Ace of 7 is approximately equal to 1.99. Ace of 8 is approximately equal to 1.99. And ace of 9 is approximately equal to 1.99. Okay, I will just add one more digit here. Okay, 1.997. Okay, Now, looking at this sequence here, right? The value of the sequence. It seems like it is increasing, but it's also approaching 2, right? As you can see the last few terms here, right? It's approaching 2. So I would say this. Number 1, the sequence is increasing. Number 2, the sequence is approaching 2. Okay, so now what do we do next? We have to show that both of these statements are true. Then we can find the limit of this sequence. So let's try to prove that, right, both of these are true first, okay? Okay, so let's prove statement number 1, okay? Prove statement number 1, okay? That the sequence is increasing. Okay, what does that mean? That means we need to show that, right? Show that a of n plus 1 is greater than a of n for all n is greater than or equal to 1. Like I said before, right? Because the first term we start with is a of 1. So n is here, right? So n has to be at least 1. It cannot be 0. Okay, so we have to show this. And how do we do that? Well, we use mathematical induction, okay? So we assume that it is true for n equals to k. Now, show that it is true for n equals to k plus 1. Okay, what does that mean? Now, if it is true for n equals to k, and it's also true for for n being 1 term higher, so basically of the next term, the next term of n, and we're writing in general. And if it's true for the next term of n as well, then it's true for all. Okay, so let's do this. So we start with a of, now, k plus 1. We will replace n with k. It's greater than a of k. Okay, so let's proceed with this. What we do is multiply both sides by 2 because we want to make it into the form of the general term, right? And then take the square root. Okay, so 2 times a of k plus 1 is greater than 2 times a of k. Okay, right? Because if this is true, then multiplying both sides by 2 is still true for this inequality. Now take the square root of both sides. We have square root of 2 times a of k plus 1 is greater than square root of 2 times a of k. Well, that's true too, right? For this inequality, if this is true, then taking square root of both sides will still be true. Okay, from now on, what do we notice? What is square root of 2 times a of k plus 1? Now notice that in the general term of the sequence, the subscript on the right side is always 1 higher than the subscript on the left side. Okay, so this is the left side. In the general term of the sequence, the subscript of the left side is always higher than the subscript of the right side. Okay, so for square root of 2 times a sub of k plus 1, is basically equal to a of k plus 2. right? Because the subscript on the left side is always one higher than the subscript on the right side. What is square root of 2 times a sub k? Right? Square root of 2 times a sub k. Well, that would be a sub k plus 1. Because the subscript on the left side is always higher than the subscript on the it's always one higher than the subscript of the right side. Okay, for this we can write that, right? This one is equal to a sub k plus 2. That's greater than this one is basically a sub k plus 1. Okay, now going back to the general term here, is a sub n plus 1, right? We use n here, right? So in this case, this is basically equal to a sub k plus 1 plus 1. It's greater than a sub k plus 1, right? 1 plus 1 is 2. Okay, so let's go back here. This is what we should be looking at, okay? So a sub n plus 1 is greater than a sub n, right? So in this case, we can say that k plus 1 is equal to n, right? So now, and k plus 1 is equal to n. So we basically show that, right? This is true for n equals to k plus 1, right? Because k plus 1 here is equal to n, and k plus 1 is here is equal to n. Then we have a sub n plus 1 greater than a sub n, which is the same as here, right? Which is what we are trying to show right now. Okay, so we can conclude that a sub n plus 1 is greater than a sub n is true for all n equals to k plus 1. Okay, since we just proved this, that means we proved that the sequence is increasing. Next, we have to prove statement number 2. The sequence is approaching 2. Okay, so let's do this here. Prove statement number 2, right? Now, basically what we have to do is show that the sequence a sub n is bounded. Now we assume that it is true for n equals to k. Now we have to show that it is also true for n equals to k plus 1. Okay? Again, right? If we're writing it in general terms right now, if it's true for the next term of n, right? The next term after n term, and it's also true for the n term, that means it's true for all of them. Okay. Now, what do we have to start with first? Now, we basically have this. We will place a sub n with a sub k, okay? Has to be less than 2, right? Because we're saying that it's approaching 2, but it's not really getting 2, right? So it should be bounded. Now let's show that this is true, okay? Again, we have to turn it into the general term of the sequence. Here. Right? So we have to multiply by 2 and then take the square root. Okay, so 2 times both sides, right? And that's equal to 2 times a sub k is less than 4, right? 2 times 2 is 4. Okay, take the square root of both sides. Square root of 2 times a sub k is less than square root of 4. And we know that square root of 4 is just 2, right? So what is square root of 2 times a sub k? Now we know that, right? From the general term of the sequence, the subscript on the right side, on the left side, is always one higher than the subscript on the right side. So we can say that square root of 2 times a sub k is just equal to a sub k plus 1. Okay? And that is equal to a sub k plus 1 is less than 2. Okay? We basically show that the sequence now we have to replace that, right? A sub k plus 1 with a sub n, right? Because based on this, what we're trying to prove here. So we're saying that, okay, for n equals to k plus 1, then we just show that a sub n is less than 2 for all n. Okay, that means we just proved that statement 2 is true as well. Okay, so we just proved that both of these statements are true. Then, what would this sequence look like? Well, let's try to draw a graph of it, right? So, let's say here. So, in this graph, this will be a sub n, and this will be n, right? And we have this point here. Let's say this is L here. So that's a number. And this is bounded, so it will look like this. It's probably going to look like this, right? It's increasing, but it's bounded by this value here, right? It will never pass this value. Okay, so what does that mean? Well, that proves that if those two statements are true, then we can say that limit as n approach infinity, a sub n is equal to L exists, right? Because when the sequence is bounded and is increasing, so it must be approaching a value. So L exists. Well, in that case, right, that also means that limit as n approach infinity, a sub n plus 1 is also equal to L, right? That also exists, right? It's the same sequence. If when n approach infinity, any term of this sequence is approaching the value L, then the next term of that sequence would also be approaching L. Okay, so with this, we can find the limit of the sequence. Now, let's come back here that we were just talking about here, okay? I'm going to rewrite this on the other side and then continue with this, okay? So here, coming back to our original question, limit as n approach infinity, a sub n plus 1 is equal to, here, square root of 2 times limit square root of 2 times limit as n approach infinity, a sub n. Now, we just figure out that limit as n approach infinity, a sub l is equal to L exists. So this is equal to L. And also limit as n approach infinity, a sub n plus 1 is equal to L exists. So this is equal to L. Okay? Then we can say that this is L, right? The left side equals to square root of 2 times L. Because this is also equal to L, right? Based on what we calculated or what we figure out. Now, let's evaluate this. L is equal to, now we can divide this into two terms, a product of two terms, square root of 2 times square root of L. And divide both sides by square root of L. That's equal to square root of 2. Now, this side is just equal to square root of L. It's equal to square root of 2. Right? Square both sides. We have L equals to 2, right? Square root of 2 squared is just 2. Okay, so that's the limit of the sequence. And of course, in this graph here, right? Basically, L is equal to 2 here. Okay, so what does that also mean? That means the sequence is convergent to 2. Hope you enjoyed this video. Don't forget to subscribe to my channel. Thank you.